One of the significant operations between vectors is the dot product, and this operation here, it takes in two vectors and returns a scalar. What that means is it does not return a vector, but just a number. I'll explain further, but the dot product between two vectors, call them u and v, or you'd say u dot v is equal to the magnitude of u, or multiplied by the magnitude of v, multiplied by the cosine of the angle between them. This is one representation of the dot product, but this is the first one that I'll introduce you to, and it'll eventually lead to this representation. When talking about multiplication with vectors, you have several things that come to mind. Firstly is matrix multiplication, in which you do rows multiplied by columns, and it outputs a vector, or a matrix. Secondly, you have scalar multiplication, in which you multiply a scalar times an entire vector, and it gives you a vector that's parallel to the original vector. Then you have the dot product and the cross product. There's probably other ones, but for now we're going to focus on the dot product and eventually the cross product. The most intuitive understanding of what the dot product is that if you were given two vectors, u and v, in this case we're going to multiply the distances that are only in the same direction, as you can see, u and v, they're not pointing in the same direction, but say I dropped an altitude from u onto v, and I only multiplied the component of u along v times v. So given that understanding, you arrive at this definition of the dot product, which is the magnitude of u multiplied by the magnitude of v multiplied by the cosine of the angle between them when they're put tail to tail. Again, the dot product outputs a scalar, and you can see this tracks because the magnitude of u given by distance formula is a number, the magnitude of v is also a number, and cosine of theta is a number itself. So you have a number times a number times a number, which outputs a scalar. So where exactly does this definition come from? U, v, cosine theta. So what I'm going to do is I'm going to drag this right triangle here when the altitude from u is dropped onto v. So when you have this right triangle, notice when you take cosine of theta, given the adjacent and the hypotenuse of theta, it's equal to this component of u along v. It is written as component sub v of u, which just means if you drop down from u onto v, the component is a scalar. This represents a distance, not a vector. But if you took the cosine of theta, it'd give you this component divided by the magnitude of u. And rearranging this would give you, rearranging for the component would give you u multiplied by cosine of theta is the component. So now we have part of the geometric dot product, but now we're just missing the v, or the vector that we've drawn our component along. So where does that come from? Right? So this value right here, it's a scalar. And all we do is we just multiply by the distance that we dropped the component along. So if we just took this whole distance and then multiplied it by that component, that'd be v multiplied by the component, which is just v, or magnitude of v, magnitude of u, cosine of theta. So that's where the geometric definition of the dot product comes from. So now that we have the geometric definition of the dot product, let's see what it actually means. So here I have three special cases of the dot product. The first one we're going to look at is when u and v are perpendicular or orthogonal, as some may say. So when you have u, v, cosine theta, when they're perpendicular, theta is going to be 90 degrees, meaning uv cosine of 90 is going to equal the magnitude of magnitude of v, multiplied by 0, which is cosine of 90. And ultimately, that would just give you 0. Therefore, when the when the two vectors are perpendicular, that means the dot product is equal to 0. This works in any case. If u was all the way down here and still perpendicular, they'd be 0. The second case is when u and v are parallel and pointing in the same direction. So when you have this, imagine these are lying on top of each other. I just do them separately because yeah, I can't draw them on top of each other. So when you have this case right here, theta is equal to 0. So when you have uv cosine of 0, cosine of 0 is equal to 1. So the dot product would just equal the magnitude of u times the magnitude of v. Okay. Now the third case, they're still going to be parallel, but this time they're pointing in opposite directions, unlike this one where they're pointing in the same direction. So here we have the angle is going to be 180 degrees, a straight angle, and cosine of 180 degrees, if you look on the unit circle, it's all the way to the left, and the x coordinate is -1. Therefore, the dot product in this case would be the negative of their magnitudes multiplied. This in all these orientations of the dot product when the two vectors are in these extreme positions. Notice where the dot product, what the range of the dot product is. So I don't know if you can see, but over here I have the inequality that comes from the nature of the cosine function itself. So we have cosine of theta is either going to be equal to or greater than -1, or less than or equal to 1. So given that inequality, if we multiply two values the same way we multiplied two values by the cosine of theta in the dot product, sorry, I forgot to write the values here. But if we multiply each part of the inequality by the same value, that would also be true given the nature of inequalities. We have AB cosine theta is going to be between -AB and AB. Therefore, the dot product, which is the two magnitudes multiplied by each other, the dot product is going to be between the negative of their magnitudes or the positive of their magnitudes. And this makes sense because, again, cosine theta, it's only between -1 and 1. And when you multiply something by that's multiplied by -1 and 1, you're still constrained to two bounds. For even more application of the dot product, in physics, the concept of work comes from the dot product between a force acting on an object and the displacement of the object. So say you were pushing a box and you wanted the most efficient way to push the box. You wouldn't really push it at an angle towards a surface. You'd want to push it along the displacement that you're moving along. And basically what you're doing is you're aligning the vectors of the force with the vector of the displacement to get the maximum work done. And again, work is the dot product between force and displacement. Also, if you're wondering, the dot product is a commutative operation, meaning that if you just switched v and u and you did the dot product of v dot u, it would give you the same scalar value. If you want to prove that, I guess, you just draw the same an altitude like you did with u onto v, but do it from v onto u. Again, this would be equal to the magnitude of v cosine theta, and then you just multiply that by u, which is vu cosine theta is equal to uv cosine theta. So yeah, the dot product is a commutative operation. Now that we have the geometric definition of the dot product, I want to move on to this representation of the dot product, which you'd hear as the component form of the dot product. Basically, if you have, in this case it's three-dimensional vectors, but if you have vectors with n dimensions, you basically multiply each corresponding dimension by each other and then add that value. So you might be asking, as I asked myself once, where does this definition even come from? It seems pretty arbitrary, just multiplying components by components. But how does this connect to geometry? You're just given two vectors and their components together. So to prove that, I want to bring up the law of cosines. And for the law of cosines, it just states that if you have two sides of a triangle and their angle between them, the distance of this third side, let's call it C, with the other two being A and B, this distance right here, the square of that distance would equal to the square of the two original sides subtracted by 2 multiplied by the product of those two distances times the cosine of the angle between them. If you don't know this, it kind of looks familiar to the Pythagorean theorem, and it could lead to the Pythagorean theorem if you just made this angle equal to 90. Cosine of theta would equal 0, and then you just have c squared equals a squared plus b squared. I want to put it into the world of vectors. So instead of a, b, and c, I'm going to have the vectors u and v put tail to tail, and this third vector right here, which would be analogous to c. This vector right here is it's the same vector as u minus v, or it could be v minus u, but in this case it's pointing this way. If that doesn't make sense, with vector operations, when you multiply two vectors, or say if you subtracting v from u is the same thing as saying u plus negative v, and negative v is just v but flipped parallel to v. So if you flipped v and you added that to the end of u with vector addition, that'd just be going this way. And that resultant vector, see how it points the same as this? It's parallel to this vector right here. So this resultant vector, it's u minus v. It's parallel to this one. So therefore, it's also, this vector right here is also u minus v. So given that, I'm going to now use the law of cosines on this triangle right here. So we want to work with distances, so I'm going to use magnitude to represent the length of each vector. So we have the square of this side right here, the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 multiplied by their magnitudes and cosine of theta. Now again, we want to show why this right here is going to lead us to this right here. We want to connect the component form to the geometric form of the dot product. Now notice in the law, given the law of cosines, we have something that looks pretty similar to uv cosine theta. So what we want to do is we want to isolate uv cosine theta here using and figure out whatever is on the other side of that. Hopefully it's going to be this. And also imagine that these are 3D vectors with x, y, and z components. So I want to do this derivation step by step. The first thing I want to do is focus on the left side of the equation, which is the magnitude of u minus v squared. First, I want to look at the magnitude of u minus v. By distance formula, we know that the magnitude of a vector is equal to the square root of the square of each component summed together. So yeah, just by distance formula. But first, know that u minus v is the same thing as saying you subtract the components of v from the components of u to give u minus v. Now, given these three components right here, what we're going to do is square each of them, sum them, and then take the square root. So the magnitude of u, and then ultimately we're going to take the square root of that. Now the thing is, this equation has the magnitude squared, so we don't actually need the square root once we take the square. So I'm just going to leave it as the sum of all of this squared. I don't know if you can see this, but expanding each of these binomials, just foiling it out, it gives the magnitude, or the left side of this equation, the magnitude of u minus v squared is equal to all of this. So right for now, we're just going to keep this and just remember it. Now I'm going to move on to the right side. So on the right side, we have the magnitude of u squared plus the magnitude of v squared. And again, from distance formula, we can just write the magnitude of u squared is equal to the square of each component summed together. So we have magnitude of u squared is equal to, now that we've expanded the important parts of this equation right here, we have a whole lot of this, but notice that there's a lot of terms that can be canceled out. So I'm going to cancel out from this side. We have x, the components of each of u and v, their square. So I'm just going to remove that from the equation overall. So I'm just going to cross these out and then cross these out. Yeah, take this whole thing out. We have this term right here, -2 times the magnitudes cosine theta. Remember, this is the part that we want because it has the dot product. The only thing that we need to take out is this -2. Now, on this left side, after we've canceled out all the necessary terms, we have -2 times x of u and x of v minus -2 y of u, y of v, and lastly, -2 z of u, z of v, which is equal to -2 times the dot product. So there's a lot of -2's in here, so obviously what I'm going to do is divide by -2, and we have x of u, x of v, plus y of u, y of v, plus z of u, z of v is equal to magnitude of u, magnitude of v, multiplied by the cosine of the angle between them. So now we've arrived at the component form of the dot product. Remember, first we started with the cosine, the law of cosines using magnitudes of u and v. Given this statement that is true, we've arrived at a statement that has to be true, which is that the dot product is equal to the component form, is equal to the sum of the components multiplied of two vectors. So that was a lot of information, but I think the main things to take away from the dot product are: one, the dot product is, it outputs a scalar, meaning that taking two vectors and doing the dot product of them will give you a number, which also means that you cannot take the dot product consecutive times. If you do u dot v and say put that in parentheses, you cannot dot the dot product with a vector because you'd be doing a scalar dotted with a vector, which is invalid. Secondly, the dot product, the best way to, the intuitive understanding is that the dot product only multiplies the parts of vectors that are along one another. Dotting u and v would only dot the components, the component of v along u or the component of u along v. Again, remember, when you push something, you want to push it along the direction that you're pushing it. You want the angle between your force and the displacement to be as close to zero as possible, because that's how you maximize the work done or maximize the dot product. In multivariable calculus, you're either going to be given the dot product, or the vectors described by the geometry, meaning angles and magnitudes, or you're going to be given vectors in terms of their components. And either one, you'd have to know how to use the geometric definition of the dot product and the component definition of a dot product. You're going to be asked to determine whether two vectors are perpendicular, or you're going to be asked to determine the angle between them given the value of the dot product. You just have to rearrange the geometric equation. But yeah, that is the dot product. Also, some applications could be with AI. You probably hear the saying that linear algebra is the backbone of artificial intelligence. And the way that artificial intelligence uses linear algebra is that the dot product, it can determine whether two words are similar. That is, if words are assigned to vectors, again, vectors are just data. So if you assign words to vectors, the dot product would determine how alike or how aligned two vectors are. So saying like telling an AI to ask like how alike are these two words, king and queen. Also another cool analogy I heard was like in Mario Kart when you have the speed boost. When you're playing Mario Kart, you want to go as parallel to the speed boost as possible, so you get the maximum speed away from it. If you went perpendicular to the speed boost, you'd be getting nothing. It wouldn't make sense. So you want to go along the speed boost.